Welcome, aviation enthusiasts. Today, we turn our focus to a remarkable breakthrough in the world of high-speed aviation, the XB-1 Boom Supersonic's bold entry into the supersonic flight development. Known as Baby Boom, this sleek demonstrator marks the company's first real-world step towards reviving faster-than-sound travel for the modern era. With its advanced carbon composite structure, triple-engine layout, and finely tuned aerodynamics, the XB-1 is more than a prototype. It's a symbol of engineering ambition and a glimpse into the future of private supersonic aircraft. After decades of silence since Concorde's retirement, Boom Supersonic has reignited the flame of Mach-speed travel with a fresh, purpose-driven design aimed at validating technologies that will ultimately shape the upcoming Overture airline. In this video, we'll take you on a comprehensive exploration of the XB-1, breaking down everything from its aerodynamic innovations and performance benchmarks to its operational cost, ownership scenarios, and financing strategies. We'll examine what makes this jet unique in the aviation world, how it's pushing boundaries, and why it matters not just to manufacturers, but also to forward-thinking private operators and investors. This isn't just a walk-around tour. It's a deep dive into the complex engineering, financial realities, and market impact of a next-generation supersonic jet. Buckle up! It's time for the definitive review of Boom Supersonic's XB-1. The XB-1 is not a commercial product with a disclosed price tag, but rather a bespoke prototype engineered to validate supersonic technology. Estimating its cost is therefore complex, though industry insiders suggest that developing and flying such a demonstrator could range between $150 million and $250 million. This figure encompasses advanced carbon composite materials, specialized engine integration, flight test systems, and sonic boom mitigation design. Because XB-1 remains a one-off asset, ownership cannot proceed in traditional transactional terms. Instead, prospective stakeholders must pursue strategic participation through sponsorship, equity, or bespoke joint development agreements. Under this model, acquisition shifts from straightforward purchase towards a hybrid investment structure. Stakeholder agreements would likely include milestone-based funding tied to demonstrator performance objectives such as Mach 1 flight clearance, flight test data delivery, and material validation results. This creates a multi-tranche commitment where funds are dispersed only as key certification or flight targets are achieved. It blends elements of commercial aircraft financing, R&D grants, and performance lab infrastructure agreements, remotely resembling government-backed aerospace development projects more than standard corporate jet deals. From the owner or sponsor perspective, defining what you own differs fundamentally from possessing a parked jet in your hangar. Instead, your value lies in collaborative access, such as flight time allocation, branding opportunities, or data sharing privileges. You acquire symbolic association with supersonic aviation, priority positioning in Boom's future program, and institutional recognition. What you don't get is resaleable aircraft equity or typical depreciation schedules. Instead, what you secure is influence over supersonic advanced aviation and a seat at the forefront of defining 21st century speed. Even without flying, owning XB-1 carries substantial fixed costs, often exceeding those of traditional business jets. Hangar storage must accommodate supersonic level temperature and pressure conditions, requiring specialized climate control and test stand infrastructure. Such a facility, complete with certified ground support equipment and security systems, could command annual fees well above $100,000. Insurance expenses are similarly elevated, calculated not only on hull value, but also on unique liability exposure related to prototype flight testing and sonic boom impact. Premiums here could range from millions, depending on coverage extent and locations of operation. Crew costs form another key component of fixed ownership outlay. Supersonic flights require highly skilled pilots certified in high-speed envelope control, paired with flight test engineers responsible for instrumentation and performance analysis. This specialized team, operating year-round, can cost between $500,000 and $1 million annually. In addition, support engineers and technical staff are needed to maintain data systems, avionics calibrations, and composite structure integrity, roles that remain on standby whether the jet flies or not. These overheads constitute a large, immutable part of the annual budget. Finally, regulatory and logistics support add to the fixed baseline. XB-1 operations demand coordination with aviation authorities administering supersonic corridor regimes, which include airspace approvals, environmental oversight, and sonic boom monitoring agreements. Such coordination typically involves recurring fees, legal counsel retainers, and lobbying activities. Moreover, data management contracts covering thermal fatigue analysis, materials monitoring, and system health modeling are required irrespective of flight hours. All in all, these fixed cost factors position XB-1 as an expensive partner in innovation from day one. When XB-1 flies, its variable operating costs are primarily driven by fuel and support expenditures scaled to supersonic performance. Equipped with 3 GE J85-15 turbojet engines, the demonstrator's fuel burn can mirror early Concorde-era usage. Current estimates suggest a fuel cost between $5,000 and $10,000 per flight hour, subject to prevailing jet fuel prices and reserve margins. Accelerated climb to supersonic altitude magnifies fuel consumption. As a result, an annual flight schedule of approximately 200 hours could make fuel alone a $1 million to $2 million burden. Beyond fuel, each flight hour demands additional expenses, landing and handling fees, overflight and airspace charges, and engine program reserves. J85 class engines often come with hourly reserve fees reaching several $100s to fund inspections, hot section changes, and scheduled overhauls. Combined with logistical costs, crew mobilization, mission planning, corridor coordination, the per-hour figure rises towards $10,000 to $15,000. Thus, at 200 flight hours per year, you're looking at $2 million to $3 million in variable expenses. Flight usage variability influences total annual cost, especially when operations mix short supersonic hops with longer subsonic legs. Short, high-thrust flights incur a higher average cost per hour, while cruising phases somewhat offset this by lower fuel burn. Still, budgeting must accommodate worst-case estimates to cover engine wear, data system activation, and sonic boom-related environmental monitoring. Ultimately, operators must plan for a flexible but steep variable cost budget aligned with flight program ambitions. The XB-1's airframe embodies supersonic precision, stretching 62.6 feet in length with sharply contoured 21-foot delta wings optimized for high-speed stability. Beneath its composite skin, 3 GE J85-15 turbojet engines deliver a combined thrust of approximately 12,300 pounds, launching the jet into transonic territory with smooth authority. The air intake geometry and fuselage shape are tuned for shockwave management, reducing drag and enhancing acceleration. Although designed to cruise as high as Mach 2.2, actual test campaigns are progressing incrementally, collecting essential aerodynamic and thermal data. Each line of flight is more than a milestone. It's an experiment in airflow control, structural resilience, and systems feedback. The aircraft's sleek profile isn't just for aesthetics. It's the product of years of supersonic optimization. In flight, the XB-1 has already achieved and sustained supersonic speeds, breaking Mach 1.122 during controlled tests at altitudes exceeding 35,290 feet. These sorties evaluate the aircraft's behavior under stress, how it handles transonic transitions, skin temperature buildup, and shockwave effects on control surfaces. Engineers are also monitoring cockpit instrumentation, verifying the responsiveness of flight software under rapid pitch and trim inputs. While the aircraft hasn't yet reached its maximum altitude potential near 60,000 feet, its current data points are shaping Boom's future supersonic flight envelope. With each high-speed run, pilot and system feedbacks refine algorithms, adjust thermal margins, and enhance predictive models. These insights form the blueprint for future commercial supersonic designs. Fuel capacity in the XB-1 is limited to approximately 7,000 pounds, placing its mission profile within reasonable testing corridors. Yet, when paired with subsonic transit legs and efficient descent planning, total range extends to nearly 1,000 nautical miles. Alleged, this operational footprint supports demonstration flights, pilot training, and technical R&D, all within controlled supersonic corridors. While it's not built for transcontinental trips, the aircraft fulfills its roles as a high-performance test platform. The data gathered here on range efficiency, fuel flow under supersonic drag, and heat-tolerant design translates directly into development of Boom's Overture jet. In practice, every flight lays a foundation for tomorrow's faster, cleaner, long-distance air travel. The XB-1 is designed for 2 crew members, but only 1 pilot seat is actually installed. The second space holds test instrumentation. Its use cases are broad and compelling, extending across corporate, academic, and R&D applications. For a corporate flight department, owning XB-1 offers high-impact media exposure, showcasing supersonic capability at aerospace trade shows, investor summits, or charters for VIP stakeholders. These flights could integrate mission science, branding, and strategic partnership opportunities. Flight departments would also benefit from hands-on pilot training in transonic flights, sonic boom management, and high-altitude performance. Academic institutions and materials researchers have a unique opportunity to embed scientific payloads or test instrumentation aboard XB-1. Advanced composites, thermal coatings, and heat-tolerant alloys can be validated in real supersonic environments. In return, governing agreements might grant data access for license holders, enabling commercial spin-offs or patentable results. Similarly, defense or aeronautics research labs could task XB-1 for atmospheric profiling and high Mach flight acquisition, leveraging its modular architecture for instrumentation removal and reconfiguration. Another practical route involves offering limited access demonstration flights to elite charter clients, researchers, or VIPs under controlled conditions. These missions, even without passenger cabin service, could involve knowledgeable observers or research partners observing cockpit dynamics and sonic boom acoustics. Such offerings create revenue offsets while showcasing XB-1's capabilities to potential future customers. In melding training, marketing, and research use, XB-1 transcends a private jet. It becomes an airborne innovation platform. Financing XB-1 diverges sharply from typical business aircraft loans, as it depends on milestones rather than predictable residual validation. An advanced structure might begin with an initial investment tranche, followed by milestone-based funding, such as achieving first flight, first supersonic run, and data delivery benchmark. In exchange, sponsors or investors gain defined rights, flight time allocation, branding placement, and data sharing privileges. Such deals resemble aerospace venture funding more than traditional asset-backed lending. Another approach involves structured leasing, where XB-1 could be leased to participants under multi-year performance contracts. Lower base payments escalate as project-wide targets are met, binding payments to technological breakthrough progress. This mitigates risk for lessors while providing investors conditional access. A dose of ownership comes with rights tied to use, co-branding, and test data, while declines in value are offset via structured agreement protections. Public-private partnerships present a third viable financing pathway. Boom or its partner institutions may enter cost-sharing agreements with government agencies eager to support supersonic R&D. In this model, public funds co-fund flight tests and expand mission scope. Sponsor responsibilities shrink accordingly, reducing private capital exposure while accelerating innovation. Such partnerships could require shared flight time, distributed data, or even public demonstrations, further aligning XB-1's mission with national aerospace objectives. The XB-1's core mission is to advance supersonic flight technology over a defined test window, typically 2 to 3 years in active flight testing. Once the flight campaign concludes, it transitions from airborne demonstrator to ground-based testbed. In this phase, the aircraft supports materials fatigue study, avionics development, thermal profiling tasks, and immersive engineering simulation. Even without flying, this life cycle stage drives research milestones essential to the development of Boom's larger Overture program. Alongside research, XB-1 may become an aerospace showcase, displayed at museums, aerospace parks, or institutional centers, highlighting its role in aeronautical transformation. Meanwhile, ownership rights tied to data derived from its flight history retain value for sponsors wishing to leverage intellectual property. Transfer of data ownership rights and models can offer decades of insight and sponsorship visibility. Thus, XB-1's legacy far surpasses its flight hours. In the broader context of supersonic aviation, XB-1 transcends its status as a prototype aircraft. It embodies a tangible shift in aircraft development, flight test methodology, and ownership model, where private, corporate, and public stakeholders collaborate. Its life cycle affords legacies manifesting as technical knowledge, institutional prestige, and cultural iconography. In short, XB-1 transforms from a flying machine into a strategic asset in aerospace history. As we wrap up this supersonic deep dive, XB-1 emerges not just as a remarkable engineering prototype, but as a bold experiment in new ownership models for experimental aviation. Through structured financing, strategic partnerships, and milestone-based investments, it enables private sector access to the frontiers of speed in ways previously unimaginable. Such costs, both fixed and variable, are undeniably high, yet they unlock opportunities in branding, data ownership, R&D, pilot training, and public visibility. Beyond its flight hours, XB-1's enduring value lies in the innovation, knowledge, and prestige it invokes, helping pave the way for commercial supersonic business jets like Boom's forthcoming Overture. The future of flight is supersonic, and it starts with the XB-1. If you're ready to ride that wave, smash like, tab subscribe, and tell us, would you fly Boom's Overture at Mach 1.7?